So today I do want you to take some more notes, and there is a new type of pattern that we're going to look at. So a reminder, so far we've looked at repeating patterns, like square, circle, square, circle, square, circle. We've looked at linear patterns, where we have the constant first difference, we're adding the same thing every time. And we have quadratic patterns where there's a constant second difference, where we're not adding the same thing every time, but we're adding the same thing to the difference. So the second difference is constant. And now the fourth type of pattern we're going to learn about are exponential patterns, or exponential sequences. So let me just give you an example of what an exponential sequence looks like, and then we'll write down a definition afterwards. So an exponential sequence might be something like this. 1, 2, 4, 8, 16, 32. I wonder if you can spot the pattern already. You probably can, but just in case. We know it's not a linear pattern. What happens if we try and look at the common difference, what I'm adding each time? I'm adding 1, I'm adding 3, I'm adding 4, I'm adding... I'm not adding 3, I'm adding 2. I can't count. I'm adding 4, I'm adding 8, I'm adding 16. That actually looks like I've just made a copy of that pattern, doesn't it? What about the second difference? I'm adding 1, I'm adding 2, I'm adding 4, I'm adding 8. It's happening again. So of course it is, because if this is a copy of the pattern, then the second difference is going to be the same, and the third difference, and the fourth difference. So this is something that happens with exponential patterns. The first, second, third, fourth, etc. differences mirror the pattern. That's one way of noticing exponential patterns. But there is something that's happening that's the same every time, right? Rather than adding the same thing every time, I am multiplying by the same thing every time. 1 by 2 is 2. By 2 is 4. By 2 is 8. By 8 by 2 is 16. By 2 is 32. And so could I do the next 3 terms? 1, 2, 3. I could. 64, 128, 256. It gets harder and harder to do them in your head, but we have calculators as well. So now we can write down a definition for an exponential pattern. An exponential pattern, and they're sometimes called geometric, but we don't really use that word for it till senior cycle. An exponential or geometric sequence is one where we multiply, not add or subtract, but multiply by the same number every time. Can you think of something really famous that's going on in the world at the moment that is a geometric sequence? The spread of the COVID-19 virus. The spread of viruses and growth of bacteria and things like that is usually exponential, which is why you can see they get big really quickly. It doesn't seem like they're increasing that quickly, but look how by the time we were at the 9th term, we were up at 256 and we just started at 1. So exponential patterns grow really quickly. Sequences grow very, very quickly. They're doubling or tripling. Okay, that's all you need to know about exponential sequences for the moment. I'm not even going to do an example with them right now. The example that we have in our book is enough. But you could try and write down an exponential sequence of your own, and I might ask you about it on Thursday. Write a different exponential sequence. Just on your whiteboard or write in your notes as an example for yourself to see if you get the idea of it. Doubling, tripling, quadrupling, all of that is exponential growth. Right, the last thing I want to do today is an example of a real world problem that involves patterns. So, once I've read through this, you might pause the video and take down the example into your own notes copy. And as we go through the questions to do with this example, you can pause it to write down the question and then come back and watch it and then fill in the notes. So in this example of a real world pattern, the height of a plant is measured. The plant is 4 centimeters tall to start, and every day it grows 3 centimeters. So notice something here. We've talked about a start and a change, and the change happens every day. Okay, so start and a change, that's how we describe patterns. So they've asked us to complete the table that's here. They said that the plant was 4 centimeters tall to start. So I'm missing something in my table. I need to have day 0. So day 0 would be where I'm starting. My start is day 0, and at day 0, my plant was 4 centimeters tall. The next bit then, after one day, it had grown 3 centimeters. So I'm adding on 3. 4 plus 3 is 7. Day 2, it grows another 3 centimeters. 7 plus 3 is 10. Day 3, another 3 centimeters, 13. Day 4, another 3 centimeters, 16. And to day 5, another 3 centimeters, bringing me to 19 centimeters. 19 centimeters after 5 days. So, the follow-on question then is, what type of sequence is this? And why did we say it was that type? Let's write out our sequence the way we're used to seeing them. We'll include the start value, 4, 7, 10, 13, 16, 19. And what we always do when we're examining sequences is we start to look at the common difference to see if there is a common difference. If there is, it will be linear. If there isn't, we check the second difference. And if it's giving me the pattern itself again, I check, am I actually multiplying instead of adding? And we can see anyway, we do have a common first difference. So this is a linear pattern. A linear pattern because the first difference is constant. So this is a linear pattern because the first difference is constant. Now, part C. So you might have to pause the video to take this down into your copies first. The question is, what is the height of the plant after 7 days and after 20 days? So we can see that the pattern should be continuing the way it has been. And we've gone as far as 5 here. So another 2, I'd get plus 3, 22. Plus 3, 25. Sorry, I had to think about it for a day. Or not for a day, for a second. So after 7 days, it should be 25 centimeters. That's enough working out there. After 20 days, am I going to go through this in my head? Well, after 7 days, it was 25 centimeters. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, did I do that right? Did I make a mistake? 64 centimeters. There has to be a quicker way of doing that, right? Well, I know that on day 1 it started at 4 centimeters, and I know that every day I add 3 centimeters, and I know that I want to have 20 days at 3 centimeters growth added on. So I could have come up with a formula like this. to get my 64 centimeters. But listen, don't worry too much about the formula right now. We're going to learn about that in second year. It is okay to just list them out like this for the moment if you find that easier. But if you understand this, it's a lot quicker of a way of finding what the answer should be after a certain number of days. The next question is this a realistic pattern to describe a plant's growth? So 20 days is around 3 weeks. And how much is 64 centimeters? That's more than half a meter. My ruler here, my big long ruler, is 30 centimeters. So something that started at 4 centimeters, would we expect it after 3 weeks to be more than 2 rulers long? I don't think we would. Now, some plants might grow like that, but I think we'd be surprised if a plant did that. Especially what would happen after 100 days? It would be 304 centimeters. It would be twice the height of a person. And we know for sure that most plants don't grow like that. So, no, because eventually most plants stop growing or slow down. They stop growing or their growth slows down. And it's quite common in maths to have a question like that to just check how sensible is the answer that you're getting. Okay, so there's the real world example of a pattern and exponential patterns, and I want you to take notes on those for today and just study your notes and make sure that you understand them. I'm not assigning you any written homework today. Okay, thank you.